John here. Let's look and see how we start up our Retro Z80 board. Okay? And by this, I mean, what do we do after the reset pulse was generated from either power on or by pressing the reset button? When we talked about that before, if you're joining this program already in progress, feel free to go over to YouTube and open the description below this video, wherein you will find a link to the playlist of all the videos in this series, so you can go back and watch the reset video if you have not already done so. Okay, so after the reset signal, what happens? We got to start up everything. The Z80 starts going. What does the Z80 really do? Well, we'll get into the finer details later, but in general, what we wanted to do is copy the contents of the flash memory into the static RAM. And this process quite often is referred to as a shadow ROM or shadow BIOS or something like that. So you can Google this if you want to understand more about the technique in different systems, but everyone's a little bit different, so be careful by using, if you're going to use this word, it may imply certain things to different people, okay, that may not match. So in our case, all we're going to do is copy the entire contents of the flash memory into the static RAM. When we're done with that, we're going to disable the flash completely, never to be seen again until the next time we reboot our board or power cycle it, and we will enable the SRAM. So the CPU will then continue to run only interacting with the static RAM in the system. All right. Now, what's the motivation for all this? Well, the main motivation in the Z80 Retro board is not, if you Google what's a shadow BIOS? Why do we do it? Well, EEPROMs are slower, relatively speaking, than static RAM. Okay, in our case, we don't care because the Z80 is more than serviced well by both the flash and the SRAM at its full speed. So we're not doing this in order to run faster, so don't get caught up in that whole game. We're doing this because the Z80 can only address 64K of memory. We don't want to waste some of that by leaving the boot ROM sitting there after we're done needing it. Okay, we want to get rid of it. We're going to discard it. Once we're done copying it into the RAM, what we're going to do ultimately is we're going to write a little program in there that will cause the Z80 to be able to load the operating system off the SD card. After it's done loading the OS off the SD card, we don't need that code anymore. We want to get rid of it and free up the memory and reuse it for something else. So our motive to do this is to give us a way simply to boot the system, number one, because we need to put some kind of a ROM in there, and number two, get rid of it when we're done with it so we can reuse the memory in our preciously tiny 64K address space. So let's look at how we do that. First, we're going to go over to the GitHub page for the project. Click on here to open up a PDF version of the schematic if you want to follow at home. Or what I'm going to do is open up the KiCad application because I find this easier to zoom in and out of than on my PDF browser, okay? So last time, what did we do? We talked about the reset circuit over here, which generates a low-going pulse or a temporary period of time on the reset signal. This reset signal is connected to the Z80 right here on this reset line there. It is also connected over here into this circuit over here, which is going to control the shadow flash memory. Okay, so this is the whole startup sequence going on right here. The flash memory and the SRAM are sitting over here. We're going to talk about these control signals down here, all right, are involved, as are the control signals here on the SRAM. For now, we're going to ignore this over here. Ultimately, this has to do with bank selecting the memory so we can actually access more than 64K in chunks of 32K. For now, let's just assume that these A15 through A18, all these signals here will just all be zero, okay? And the reality is you'll find out when we get there that they will be all zero when we first boot up the system, okay? So back to this up here, all right? So the main gist of what's going on here. As we know, temporarily, this reset signal with a bar over it goes active, low, briefly when the power goes on or whenever you press the reset button. Whenever that takes place, this is a NAND gate, so with one of its inputs is 0, it doesn't matter what the other one is, this must be high, period, okay? Then down here, this high comes around down here, So this gate here is a high, and we don't yet know what's over here. For now, let's assume this is a 1, because it will be when the thing boots, and we'll talk more about this later, okay? So if I go by my word that IOREC 70 is high and reset is low, we know this is high, comes down here, a high ended with a high is a high, with a not is a low. So this thing becomes low at that time, comes back up around to this AND gate up here. So now this AND gate has 2 lows on its inputs. And that doesn't change anything, because as long as either one's a low, this is a high. Later on, the reset signal goes away, becomes high. This doesn't change because this low that came through here holds this thing into a false AND operation, which keeps this thing high. So this thing reaches a quiescent state where SRAM cell is a 1 or high, and flash cell is low. And it will stay in this state forever unless and until IOREC 70 here becomes low. And as I said before, this does not happen until later, under control of the CPU by code that we will write down the road, okay? So in this particular state, then what's really going on? If SRAM cell is high, no matter what, we know SRAM OE over here is always high, without regard to what's over here, right? If flash cell is low, which is what happens in the reset state here, then the flash MREC over here will depend on the value of MREC over here. And as we know, MREC goes low. It's controlled by the CPU. Whenever the CPU wants to read or write and exchange data with a memory. So with flash cell low and MREC high, flash MREC will be high. Flash cell low, MREC low, flash MREC will be low. So what does this really mean? After reset, the MREC signal will simply appear over here on flash MREC until this becomes high. At which point in time, this will never go low again. Okay? So we're going to see, let's see what's happening down here with regard to the flash, all right? As the name implies, that is the MREC signal that's propagated into the flash down here. Now, the way the flash memory works is it has, now, keep in mind, this is a programmable flash, and therefore, we can write data into the flash and we can read data out of the flash. If you read the spec sheet, and we'll talk more about how that all works when we talk about the flash programmer later on in this series. The way it works, the short of it for now is that unless you write a very specific pattern of bytes in a specific order to a specific set of addresses in the flash will never receive any data. It will never be writable. Okay? So the short of it is it's okay to write garbage into the flash because the flash will simply ignore it until we enable it under software control. Okay? So for now, it doesn't matter that the write signal, which comes directly from the CPU down here, and this is pretty important to the startup process. These are the CPU that generates the read, write, MREC, and IOREC. We talked about that before when we went over the signals from the CPU, right? Okay, so what we're doing here is we got the read, the write signal from the CPU, the read signal from the CPU, and for all intents and purposes, right after the reset, this is the MREC from the CPU. Okay, because that's what this circuit up here does. It says flash MREC equals MREC as long as flash cell is low, and we already went over how that happens and why that happens, okay? So really what's happening after the reset is the Z80 has full access to the flash, puts out its addresses, and it can read from the flash. In theory, it could also write to the flash if it was told to do the right thing in the right order and write the magical signature super sequence into the magical addresses to enable the flash to be able to be modified. We can do all that when we're in this state, okay? What we're going to take advantage of is the fact that the Z80 can simply read from the flash, okay? So when we're in this mode, and we're going to find out in a minute that this is going to cause the SRAM to not play a role in what I'm about to talk about, this SRAM OE over here. We'll get there in a second. When the board first boots up, we have MREC read and write in here. And the Z80 will simply read instructions one at a time, starting at address 0. And we'll put a program in the flash that starts at address 0 that'll be executed by the Z80 after the reset. It's as simple as that, okay? What that program is going to do, as I said earlier, it's going to copy the contents of the flash memory into this static RAM chip over here. When it's done making that copy, what it's going to do, the Z80 will toggle this line right here. IOREX 70, it'll set it low briefly, at which point in time, that guarantees that this has to become a 1. It used to be a 0, now it'll become a 1 because at least one of the inputs of the NAND is false, therefore the output is 1. It'll propagate up and around to here. Reset has long since become 1. By definition, the Z80 cannot be executing code if reset is low. Therefore, we know if this happens, we have a 1 and a 1 here, which changes this to a 0. The 0 propagates down and around down here and keeps this gate output in state of a 1. All right, so that later on when the Z80 removes this signal and it goes back high again, this one down here will be still a 0, therefore keeping this a 1, keeping these both as a 1, and that is a 0. Okay, this is an RS latch. Google it if you need more information than that. Okay, so once the Z80 pulses this thing, this goes to a 1 and stays a 1 for the rest of eternity until the next time the system is reset. Once this becomes a 1, this can never become 0 again. All right? And because that flash MREC is connected up to the enable pin on our flash, it will disable the flash, keep it disabled forever until the next time the system's reset. It'll put the flash, quite frankly, into a low-power standby mode offline, okay? Never to be seen again. Okay, now, because we know that once flash cell is high, SRAM is low, we kind of play the same game over here. SRAM OE will be low then when read is low, and SRAM OE will be high if read is high. That's what an OR gate does. If one of the inputs is a 0, it simply copies the other input over to its output. Okay, so SRAM OE, we sort of saw that a minute ago. That's right here. And let's look at how the SRAM works. We got address lines, we got data lines, and these 3 control lines. That's it. Let's zoom in on this. What happens? Let's look at both of these together if I can get it all on the screen at one time here. Okay, when the system first boots up, we know that SRAM OE is always a 1. Flash MREC copies the MREC. We just went over all that, okay? Once the Z80 pulses that IOREX 70, this becomes a 1 and stays a 1. This becomes a copy of the read signal. MREC is always hooked up to the SRAM, so no matter what the Z80 does, if it ever interacts with memory, MREC will be low, it'll be true, which is connected up to the chip enable line on the SRAM. So even when we're reading data out of the flash, when flash MREC is true and it's low and we're reading data out of here and executing instructions, we're also enabling the SRAM, but because we never enable SRAM OE during the startup, the SRAM never outputs anything on the data bus. When we're executing code out of the flash, and we want to execute the logic that copies data out of the flash and into the SRAM, the Z80 will assert MREC. Okay, it will also assert the write signal. And that will be interpreted by the SRAM, and the SRAM will accept and store the data that came from the Z80 during that write cycle. And as I've said before, actually at the same time, the flash will also receive the write data. And of course, it won't store it. It won't cause the flash to reprogram itself because we didn't do the magical startup sequence to enable the ability of the flash to program itself. And even if it did, well, it just so happens it would write the same data back into the flash that it read anyway, so that's not a big deal. And we'll see how that kind of happens in the code later on. The short of it is, when we're reading from the flash and we're writing back into memory somewhere, let's say, we're writing it into the SRAM, because what does it mean to write to memory but to assert MREC and assert write at the same time? That'll wake up the SRAM, and whatever address comes in on the address bus and data comes in the data bus will be stored in the SRAM at that address in the address bus, okay? And now we know that after it toggles the IO-REC 70, the OE is connected to the read line, okay? Once that happens, if the Z80 reads from memory, MREC will be low, this will be low, and the SRAM will react. It'll get the memory, the data out of the memory at the address on the address bus and send it out the data bus over here, okay? And because during that period of time, we know that flash MREC is high forever and never will go low again, the flash will not conflict with the SRAM and try and output data at the same time, okay? In other words, there won't be a bus conflict. All right, so that's how we're going to start this system up. Start it up. What happens is Z80 reads anything it ever reads, it sees the values out of the flash. Every time the Z80 writes anything, it'll be writing into the SRAM. It's as simple as that. Okay. Later on, it shuts off the flash. All reads come from the SRAM, and all writes still go into the SRAM. Okay. That's what this circuit here does for us. Now, let's look at this IO-REC 70 over here. How the heck does that happen? Why does it happen? What does it do? Well, that has to do with this over here, this IO port decoder. Now, in order to save money, what we need to do is be very careful about how we kind of reuse things, and we have to be as clever as we can about not doing things that require us to add more chips to the design. We want to do this with the least money as possible, smallest PC board as possible, and get as much functionality as we can all at the same time. Let's look and see what this chip does. Among other things, it generates this IO-REC 70 signal right here. Okay? This is HC138, which is a 3-line to 8-line decoder. And by that I mean, if you enable the chip with putting the right values on these signals over here, and we'll talk about that later. Once it is enabled, the 3-bit binary number that comes in on AO1 on AO2 here, right? Ignore where those go to for a moment. If we enable the chip, we take the 3-bit binary number here. That will be 0 through 7 in decimal. That determines which one of these 8 outputs, 0 through 7, will be set to a low. Okay, now this chip, whoever created the symbol for this, they use this slanted bar. That means the same thing as the bubble over here. It's nice to have 87 different standards so that you can always pick one and mix them all the time so that no one can understand your designs. Okay, I don't find that pleasant, but it's just the way it is. Anyway, so yeah, that's what these little triangles mean there as well as over here, okay? So these means that these are inverted outputs. So if I put a 0, 0, 0 in here in binary, that means output number 0 will be low and all the rest of them will be high. If I put a 1, 1, 1 on these 3 address lines, that means output 7 is low and all the rest of these are high, okay? Now let's look at the enable logic in here. Remember, when I talked about the IO-REC signal and its relationship to the M1 signal, oopsie, I'm editing the schematic. I don't want to do that. That's, of course, the the downside of opening this with KiCad. I just won't save it when we're done. Remember the relationship between IO-REC and M1, okay? Now, that relationship is that when the Z80 wants to exchange data with some sort of an I/O device, it will set M1 high and I/O rec low. Look at how we hooked it up to the enable lines on the 138. We hooked up the I/O rec to this enable 1 over here, which is active when it is low. Okay? So as long as I/O rec is a 0, that means this pin here is true, and we're partially enabling this 138. Okay? As long as A7 is 0, this one will be also true. That's good. If M1 is high, meaning we're not doing an opcode fetch cycle or an interrupt acknowledgement, and the I/O rec is low at the same time, then we are seeing the Z80 trying to exchange data with an I/O port. So when M1 is high, this is true. When A7 is low, this is true. And when I/O rec is low, this is true. What does that mean? I/O operation that's not masquerading as an opcode fetch to some I/O port address where A7 equals 0. Okay, that means any I/O port less than hex 80. Okay, we'll enable the 138 here. Now, which one of these gets active? Well, that depends on A4, 5, and 6. This is what we call a partially decoded address. We're going to look at A7, 6, 5, and 4. If you write out an 8-bit number in hex, this would be the first digit of the hex number on the address bus. Remember that I/O ports have addresses that start at 0 and go up to FF. Memory starts at 0 and goes to FFFF. Okay? So therefore, I/O ports all have an address that has 8 bits. Memory have a 16-bit address, all right? So what is this thing doing? It's looking at that first hex digit of the 2-digit address of all the I/O ports. That's what this thing over here represents in my notation. If A7 is a 0, because it has to be to enable this chip, and A6, 5, and 4 are all set to 1, this 4-bit binary number comprised of A7, 6, 5, and 4 is then 7, which is 0, 1, 1, 1, right? That's I/O rec 7, 0. I probably should have called it something like I/O rec 7X, okay? Because this pin will be true, or low, in other words, if the Z80 does an I/O operation involving addresses 7, 0, 7, 1, 7, 2, 7, 3, on up through 7F. Right? Because it ignores A3, 2, 1, and 0. It only partially decodes this address, all right? So these things over here represent the first of a 16-byte address range representing I/O ports to the Z80. So if the Z80, tries to do a read from port 70, or if it tries to do a write to port 70, this signal here will go low during the period of time that the processor is trying to exchange data with port 70 or 71, 72, on up through 7F, okay? So then what does our boot algorithm really look like? And again, ignore everything else in here. All we care about is this one signal. The only thing that governs the value of this signal are these lines here. Ignore everything else, okay, for now. So I/O rec 70 goes low if and only if the Z80 is trying to transfer data to any I/O device in that address range starting with 7. Okay? And that's what we're going to do. We're going to write a little program that runs starting at address 0, because what the Z80 does, it starts reading from memory at address 0 after it gets a reset signal. One instruction at a time, and does whatever it says. It'll get all those instructions out of the flash. Those instructions will go into a loop that reads in the contents of the flash, copies it into the SRAM by literally reading the 1 byte at a time from address 0 and then writing the data back into address 0. Because when it reads, it's reading from the flash. When it writes into the SRAM. And if you copy bytes from address 0 through whatever, 64K if you want to, and then write them right back over themselves. It'll copy the flash to the SRAM in place. When that copying is done, we just simply read from port 70, which causes this thing to flip. No longer talking to the flash. Start now executing out of the SRAM. Okay? And you're not going to pull the rug out from under the feet of the Z80, provided that you're careful. Okay? Make sure you copy all the code from the flash into the SRAM. Because as soon as you touch port 70, you've just gone into Hotel California. You're never coming back out of there. So you need to make sure you copy the program that the Z80 is currently executing along with anything else you might want. Because once you shut the flash off, you immediately start executing out of the SRAM without any concern whatsoever as to whether or not there's actually useful instructions at those addresses. All right, so what we're going to do is literally just read in one byte at a time for the bottom region of the flash, writing it into the SRAM, and then poke port 70, and that'll be our jump to light speed, as it were, and we'll be running purely out of the SRAM. That's how we're going to start this thing up. From there on, hopefully, it's all downhill. So thanks for watching. I'll see you next time.